So welcome and thank you for coming and watching what we're talking about. I'm going to introduce GreenWaves Technologies. We are a fabless semiconductor startup company based out of Grenoble in France. And we design processors based on RISC-V cores, which are really focused around doing AI and DSP on very, very energy-constrained devices. So when I talk about energy-constrained devices, think about things like earbuds, headphones, sensors that need to last for a long, long time on a single battery. We have offices in Bologna, Italy, and Shanghai in China. Our office in Bologna is very closely related to the University of Bologna, and we have very strong partnership with a couple of universities, the University of Bologna and Zurich, University of ETH Zurich. Those two universities jointly have a program called PULP, which we are one of the founding members of, and that is really focused on using parallelization to achieve very, very low power energy consumption in these kind of chips. We have one product which is in production, has been in production since 2020, which is GAP9, and we have a product which we have chips back and out to customers called GAP9, which will be in production at the end of the year. So our markets, as I mentioned, it's really a combination of neural network, of classic DSP, and of ultra-low latency DSP. So ultra-low latency DSP means processing sample by sample in real time at, say, 768 kilohertz. So like 1.3 microsecond processing delay. And where do we use that? Well, in areas which kind of either use one or a blend of those things. So data interpretation, like object detection, scene detection, face, voice ID, transforming data, so transforming audio, perhaps denoising audio or putting effects into audio, and also actually in certain image applications as well. And then applications where we do hybrid things. So, for example, steering an active noise cancellation system by using a neural network. So there you need this combination of ultra-low latency sample-by-sample processing, because otherwise you can't do the ANC, but then steered in terms of its adaptive strategy by a neural network. And then pure DSP type stuff, like spatial audio, for example. And this is focused, as I said, into IoT sensors. And you can see on our stand there a small IoT sensor from a partner in Germany that actually takes an infrared image of a room and counts the number of people in it, and wearables and hearables. So our latest product, GAP9, really combines this capability into a single product. So we combine this real-time streamed autonomous time domain digital signal processing as something we call a smart filtering unit, which is a dedicated hardware block really focused on that. We combine that then with an ability to do general digital signal processing, or something we call a cluster, and I'll talk about that a bit more, and highly flexible neural network processing done on a combination of our compute cluster and a neural network accelerator that we call NE16. All of this happening very, very low power. And when I talk about very, very low power, our power budget is in microwatts or milliwatts. It's not in watts. It's not in hundreds of milliwatts. It's in ones or tens of milliwatts and in hundreds of microwatts in terms of processing power. So really focused on very, very, very energy-constrained devices. So we're not low power in the sense that we do a load of calculation at a few watts. We're very low power in the sense that we're compatible with devices that are either using harvesting or using batteries. And then finally, and very importantly, very flexible. So flexible to meet the needs of different types of neural network architecture, different algorithms that we might want to do, be they classic DSP algorithms or DSP type tasks, or neural network tasks, be they transformers or recurrent or convolutional or whatever they might be. And fairly easy to program versus alternatives. There is no easy to program embedded computer. I don't really think that exists, but because always there, it's a single chip and observability is always an issue. But it's quite an easy structure to program. So what does it look like? So this is a bit more complicated, and I'm going to go through this very quickly. But fundamentally, GAP9 breaks down to two bits: an MCU and a compute cluster. When I talk about compute cluster, we think high power computing, like HPC type stuff. Well, it's very similar. You can actually even program it with OpenMP. So if any of you are familiar with high-power computing, that's a structure which a compiler kind of library tool that allows you to actually do parallel loops and things like that. On the left-hand side, we have a very rich set of interfaces. We have a controller which controls all of those interfaces in a very intelligent manner, which allows us to do a lot of offloading of processing while we're dealing with the interfaces, which again reduces power because getting information in and out is part of the power equation. And then we have this block called the SFU, which is this time domain filtering unit, which I'm going to come back to. Then we have a core, which is a RISC-V core, and one of the nice things about RISC-V is it allows us to modify the instruction set, add new instructions. And we do that in 4 different domains. We have DSP type instructions, so max and saturation and clipping and things like that, hardware loops. We have a bit manipulation engine in each core, so we can do things like shuffles and pop counts and things like that. We also have a vector unit in every single core, so we can do 8-bit and 16-bit vectors. And we finally have a new thing in GAP9, which is this TFPU, which is a trans-precisional floating point unit. So we can do floats in 32-bit, but also in 2 different 16-bit representations. So IEEE 16 or bfloat 16. bfloat 16 is super interesting for neural networks. If you're familiar with it, it's basically like an IEEE 32, but with much less precision. So you keep the same range, more or less, same exponent, but the mantis has much less precision. And that's super interesting for neural network stuff. And that is compatible with the vector engine. So we can do vectors of 2 of those in the core. So that's kind of like, then we have a memory area with, either something which is very big or something which is very small, depending on how you look at it, but 1.5 megabytes of RAM, 2 megabytes of EM RAM, and then very rich interfaces for images or for sound. So this actually, from a sound interface perspective, we have 48 channels of sound coming in, so 3 SAEs with 16 time slots on each. Then, on the right-hand side, a cluster. So this is actually 9 RISC-V cores with a shared memory area. All of the synchronization of these cores is handled in hardware. So we do all of mutexes and barriers and things like that, and forking, joining, and so on in hardware. Why? Because that allows us to be very fine-grained about the way that we can actually parallelize things. You can think of this like a parallel compute machine, like hardware threads. That's essentially how we use it. So you parallelize things in lots of different ways on here. And then all of the memory movement across this fabric, be it external, internal, or cache, is handled manually. Well, handled manually from the hardware perspective. But in software, we have really powerful software tools that allow us to model kernels, model all of the memory movement, the data movement across that, and actually generate the code automatically for all of the data movement. So we use that very heavily in terms of scheduling properly the way that kernels run on this device. Just one quick statement on the smart filtering unit. I'm not going to go into the details of it, but really, why are we doing this? Well, because we really want to be able to do very low latency for ANC type applications, have a very low power, so use a structure which is dedicated hardware, which allows us to have very low power consumption for these kind of tasks, and a fully deterministic execution time, so we don't disturb it in any way from the other bits of the chip. So it's basically something that can handle multiple different filtering graphs for audio, really primarily focused on audio, very primarily focused on ANC, but can be used for offloading, special effects, audio effects, heavy-duty filtering, like an equalizer or something like that. All of that can be handled by this single IP block. Super configurable. You can change all the parameters of all these different blocks, has built-in sample rate conversion capabilities, multiple clock sources. It's a really, really powerful component, which I could spend an hour and a half or 2 hours on just in itself, easily. So how does this big, and this is really, I think, where I really want to spend a little bit of time, how is this cluster plus SFU thing different to what a DSP is now? What one classically thinks of as a DSP chip. A DSP chip, generally very long instruction word type chip. So you're relying on the compiler to schedule a load of things to happen at the same time. And very often the compiler fails. So you spend a lot of time trying to manipulate stuff and perhaps going to assembly code to try and get the thing to be properly scheduled so that you really get a good performance out of your DSP. In GAP9, we have a combination of two things. A cluster, which is really 8 free-running cores with one cluster controller core that we use mostly for controller-type tasks. So 8 free-running cores, but that are synchronized in hardware, which means that they can desynchronize a little bit. So we don't have the problem of trying to schedule things at the same time. And once one of these cores is finished doing its work, it's clock-gated, one cycle later. So it's not using any power. This really allows us to be really flexible about our synchronization schemes. We can synchronize things, we can parallelize things by having all of these cores essentially doing a SIMD type approach. So same loop, different data, but desynchronized inside that loop. Or you can pipeline them. So if you have something where the next result relies on the previous one, you can process a pipeline of samples and synchronize all of these cores using a lightweight semaphore. And then we combine that, looking after the 20% of those instructions that are generating 80% of the power, we go after those with the NE16. So really focusing on convolutions and map moles and things like that, which are really the power consumption elements of a. But having all of this flexibility of real programmable cores. And then we combine that with the SFU, which is really 4 autonomous filtering units, doing sample-by-sample filtering, super high bit precision, but manipulatable in between the two of them. So this can pre-filter stuff, running it to the cluster. The cluster can produce results which change the filtering patterns used by the SFU. And this combination is really what makes the structure really, really interesting for our customers. What does it do in real life? Well, having these synchronized free-running cores, we've done some comparisons on an LC3 codec. LC3 is the new Bluetooth low-energy codec. And we've done an implementation on the GAP cluster from the specification. So it's license-free. We'll be giving that to all of our customers. And we've compared the power consumption of that versus a Hi-Fi 5. And we see 2 times less cycles and 3 times less power per operation. So 6 times more energy efficiency versus a classic DSP structure on really what is a DSP-type task, like a codec. We have a whole range of development tools. You program GAP9 with C, C++, GCC. It's a very, very classic set of development tools. As part of our SDK, we have a full SOC simulator. So you can simulate not only the cores, but also things external to the actual SOC, the whole SOC itself and things external to it. And a profiler which ties into that, which gives you a visual idea of what's happening inside the chip, which is super useful. We have a full set of neural network development tools which go from PyTorch, which go from TensorFlow and take you all the way through to running code on GAP with a large level of support of different types of neural network kernels. So as I said, convolutional, transformers, recurrent, even custom kernels and custom elements in that. And then a full set of audio tools which link to things like MATLAB, where you can simulate your filters and so on and so forth, and produce code for GAP. So what are our customers? One last thing, we have an EVK, which with 3 levels to it, with a module, which you can see on our stand and understand more about. So what are our customers actually, partners doing with GAP? So this is one example of that. This is a product you can see on our stand as well. This is a sensor with an infrared sensor inside it. All of the image interpretation is done in the sensor. So in here, so from a privacy perspective, no image goes off it. And from a network transmission perspective, data transmission perspective, what it's transmitting is either the coordinates of these boxes or a count of them. And this box allows you to last for 5 years on a few batteries which are inside the box. So you just put it onto the ceiling, and then that gives you the ability to count the number of people in a meeting room, to find out if a desk is occupied or not, to go to a cafeteria and see, is it busy, is it not busy? Am I using this space well? Am I not using this space well? Is the comfort good for the people inside this building, and so on and so forth. On the EP stand, there's one demo that we're working on with them. This is actually being able to do people detection and counting tasks on images from a sensor that they're using energy harvesting. So in that case, the sensor then doesn't need to be recharged, doesn't need new batteries. It just works forever, within the limits of the hardware, obviously. In the audio space, we've got a number of partners who are doing really, really innovative things in terms of sound processing with GAAP. This is a very traditional DSP type task. It's actually spatialization of sound using an IMU that's inside your headset. So that tracks your head. And then you have maybe a stereo source or even a multi-channel source. And in real time, we render that sound just like you'd render an image, but we render sound and position those sounds in the space that you're listening to. And because your head is moving, your perception system really picks up the fact that that sound is, because when you move your head, it moves the speaker source. And that gives you a really good, tricks your perception into seeing the sound is spatialized. And it's completely different to the old stereo sound button on things, spatialized like dynamic sound type buttons. It gives you a completely different effect. Then we have a French company, Aura Sound, who's doing great work doing AI-steered active noise cancellation and noise reduction systems, AI-based noise reduction systems for improving intelligibility of audio signals. Again, ultra-low power consumption and a breakthrough for hearable type products. This is one which I particularly like because it's very forward-looking. This is a company called Algocia. They are doing a system which uses brain signals, so EEG signals, and then a separated source of sound. So if I'm listening to, say, three of you talking, I separate the three of you through a separation system like beamforming or something like that. And then I feed those three separated sources plus the EEG signal into a neural network. And the neural network tells me which one are you trying to listen to. And by trying to listen to this one, so if I'm trying to listen to you, I can slightly augment that sound and listen to you better. And then we have this demo on our stand. This is a company called Cyberon. They do a wait word system, keyword spotting system. One of the nice things about this keyword spotting system, it can have quite a big vocabulary, so you can have 30 or 40 things that it will recognize, which can be phrases. But the nice thing is it's phoneme-based. So to retrain it, you don't need a new set of data. You can actually just feed the words that you want it to know, and multilingual, it will actually retrain the network automatically to understand those words, which means it's very simple to produce maybe customized keyword spotters for certain applications. So that brings the end of my presentation. Thank you very much for listening to me. Our stand is just here, but if you have questions now, I'm happy to answer them as well.